So thanks for coming, everybody. Some traveled short, some traveled far. Again, my name is Amy Reed. My presentation is titled Comparison of Irrigation Water Use Estimates Derived from the Modified Blaney-Criddle Model and the Operational Simplified Surface Energy Balance Model in Southeastern Arizona. Whew, mouthful. So just like anywhere, you need water if you're going to live in Arizona, but it's particularly hard to find because we live in a very arid environment. So we need to make sure that we have access to dependable and adequate supplies. And to do this, the water managers of the state need to know how much water we have and how it's being used. And so they have two sources that they look at. We have our variable surface water, and that comes from rivers and is variable because rainfall is variable. And then we have the steady groundwater. It tends to stay the same because it takes a long time to replenish, which is why it's called non-renewable. And as you can see from the graph, about 60% here in 2010 came from surface water. So this is an example of where our surface water is and where our groundwater is. And the white wells, all these little tiny dots all over the place, are exempt wells, which means that they pump less than 35 gallons per minute, which means that if they're required to report, they are exempt from reporting. So the study area that I want you to keep in mind kind of through the rest of this presentation, how it relates to the surface and groundwater, is highlighted in red. And the management areas that I had mentioned about reporting, we have the purpley pinkish ones that are active management areas where you have to not only report your water, but it is also regulated on how much you can pump and where. Then we have the green areas where the water is monitored, but there is no regulation on how much can be pumped. So go ahead and peruse the agricultural areas while I tell you what's going to be coming up next. So I'm going to be talking about the dilemma, the study and its components. I will give you a summary of my project, and I will do some acknowledgements, and we'll have time for some questions. So the dilemma. Groundwater use needs to be planned for, so we need to know how much it is, but it's not required to be reported. In addition, there are not a lot of information out there that says how water use, or what you can use to estimate it. Hence the study. So within the study, I have the question, how are we going to estimate the water use, the parameters, the methods that were used, the results, and my conclusion. So the focus is irrigation because, as you can see, it is the largest user of water in Arizona. It's followed by the municipal or municipal population, but irrigation is by far the largest user. So how are we going to estimate it? The study covers, the study area covers Cochise County and Graham County. The study basins are these basins in lighter color. And if you recall from the earlier map, one of them is required to report. But this is also self-reporting based on either an actual meter or a calculated value. So the study was done on 3 groundwater basins over 3 years, and it used the Modified Blaney-Criddle, which will be known as MBC, and the Simplified Surface Energy Balance Model, which will be known as SSEBop. It was done at a field and a scale level, or field scale and whole basin level. So in Cochise County, which is where the majority of the study is located, they are almost exclusively dependent on groundwater. The only surface water that comes through Cochise County is right here. And as you can see, half of it is dark blue and half of it is light blue. The light blue is an intermittent stream. It does not run all year. So they have very limited sources. It's also a very large agricultural center, and the population is fairly low. So most of its use comes from irrigation. Every piece of data was projected into NAD 83, Zone 12. So the first method, Modified Blaney-Criddle. Modified Blaney-Criddle is an empirical model, meaning that they actually did studies to find the relationships that they're computing. So they require latitude, monthly temperature, monthly precipitation, crop type, and planting and harvesting dates in order to have the model work successfully. Then you get an output from the program that was designed for us to put all this information into, so we don't have to calculate it all by hand, because that would take a long time. So this is an example of the output, and above it is the formula that you'd have to use for every single crop type, every single field. So for the data collection, we need to know the crop type. So we literally go out into the field, and we take these big old maps, and we drive around all over Arizona and mark down what crop is on each field. These are young pecans, and what irrigation system it's using. Because the ultimate goal is to find out how much water is withdrawn. So we go by groundwater basin, which is why these studies are based on that. And those are defined by the ADWR, or the Arizona Department of Water Resources. While we're out in the field, we also check the planting and harvesting dates to kind of ensure that we're still on track, and we use research from various institutions. And the temperature and precipitation come from the Arizona Meteorological Network, the National Oceanic Atmospheric Administration, and the Parametric Evolution Relationships on Independent Slopes model. I got a lot of tongue twisters in here. So method number 2, the SSEBop. It's an energy balance model, which means that it considers all the energy that is brought into the earth from the sun, the large yellow arrow, and how much leaves the earth. So you've got the red arrow that goes up, the soil index, which goes, or soil heat going down, and the difference between the two is essentially your evapotranspiration. There are a few other kind of things that are in there, but they're kind of negligible. So to get the evapotranspiration, we need a reference ET, so you need to know how much does something evaporate. In most cases, it's grass or alfalfa. You need to know the air temperature, the albedo, particularly in the west where you have high reflective surfaces, and ideally 2 satellite passes if you're going to be looking at crop rotation. And then the precipitation. All these can be in a gridded format because the satellite data is in a gridded format. Your output is what you see below, the evapotranspiration. And this little piece here comes from just below the Wilcox playa. So the comparison of the two models. I took the output that you saw on the earlier slide, and I ran it through this model, and using the feature statistics to table tool in order to pull the exact evapotranspiration from each agricultural field, and then recalculate it because it is processed in millimeters, recalculate it so that it meets what the Blaney-Criddle is processed in inches. And eventually our goal is to get to acre feet. So once the tool has processed everything, the ET is rejoined back to the agricultural fields. And you have the data elements for the comparison. The verified crops. We used the satellite images so you can kind of compare the differences between and make sure that all the crops were accounted for. And then this is the output of the ET. The more blue it is, the more water there is. And you'll see some areas like this, which is where the aerial images come in handy. You can see it's kind of like a ravine area. And then this is an evaporation pond, which you can also see right here, which is one of the reasons you still need to know where the agricultural fields are. So what were the results? In a basin-wide comparison for the 3 years, 2012, 2013, and 2014, the model showed relatively good agreement. The percent change was between 1 to 20%, given the various areas and the various years. One of the outliers that you can see, the San Simon area. Best guess as to why this has occurred, Modified Blaney-Criddle assumes that all fields are irrigated to the same level with water and that they have the same level of growth across the entire thing. San Simon has been changing a lot in what is being grown there. It's gone from a lot of alfalfa to a lot of orchards. So there's a lot of new plants. Some of them are younger, some of them older. So you're getting these variations based on Modified Blaney-Criddle giving you one consumptive use for a plant range that's ranging from 0 to, I believe we cut off at 5, and then we do another one for 5 to mature. So that's where we're seeing some of the differences. Then I compared on a seasonal basis because I wanted to see, is this going to be, good comparison across the entire year? Is there some area that we really need to drill down on? You can see the comparison is fairly good. However, January through June, we found that the comparison was off by a bit. Best guess for this is that the planting dates for Modified Blaney-Criddle are affecting the calculation of that ET. And this is because, let's face it, not every farmer is going to plant their corn on April 4th, and they're not all going to harvest on October 7th. So we're going to have variations. And it's very clear in this map that the main planting and harvesting season, where things really start to overlap, is where we start to see the big discrepancies. So this is an area for further research. I also ran it by crop type to see, is each one getting the same level of congruency? And the alfalfa, the corn, they do pretty good, but you can see that the barley, not so good. So another area of further research. Why are these crops, some of them working really well and others not? So in conclusion, choosing the right model depends on the available data to you, the time required. If you're going to do an entire state, it's much easier to do an aerial satellite-based one. If you're just doing a small area, having somebody go out and verify crops is not so bad. The components that you want to study. There's obviously some areas that SSEBop does better and others that Modified Blaney-Criddle does better. And you can see here the number of factors that affect crop growth. So you really have to understand how each model is affected by these and what you want to look at. Other things to account for. Models don't account for everything. So if you're looking at withdrawals, losses before and after the field, how are you going to account for that? Variations in crop type. Crops are planted in different manners, and so that may affect how the models are actually recording things. And then the irrigation system. If you've got a flooded irrigation system, you're withdrawing much more water than if you're using a drip irrigation system. The other thing is how each model is affected by the stage of growth. You can see the vast difference between the very beginnings and when it's fully grown. And here, inconsistent growth. Obviously, Modified Blaney-Criddle may not catch that because it's assuming that even field, where SSEBop catches this. So, in summary, groundwater is in high demand and it's limited, and we need a good way to estimate it. There was one area in Arizona that I looked at, so more studies need to be done to cover the entire state and potentially the entire West. Irrigation was the focus because it is the largest user in the state and pretty much the country. Modified Blaney-Criddle and the operational simplified surface energy balance model compared to each other very well, depending on the circumstance. And all the factors that go into the study, the growth, everything, determines which model is going to be best. So it's really dependent on, it's a specific, which one is going to be best. So I would like to thank the staff at the USGS for their help with the data and processing, knowledge, MSGS team for everything that they've done to help support me as I've moved through the program, my family and friends that are spread out everywhere, and the photo credits go to Saeed Tadian and Brandon Forbes of the USGS. Questions?